So I'm going to start teaching the class. So let's go ahead and look at this first problem here. So optimization problems are word problems, real life problems, where we try to get the best of a given situation. The optimal solution may be the maximum or the minimum depending on the context of the problem. So let's look at an example. And we're going to see kind of some themes that are almost always true when we talk about optimization problems. So here is the first problem we're doing. A farmer has 120 feet of fence. And wants to build a corral for his animals. To keep the horses and I forget what kind of animals we got here. So to keep the horses, and I want to say sheep, no, cows, and cows separate, we need a dividing fence as well. So the question is, how should we construct the corral so that we maximize the area? Right? We would like this corral to have as much area as possible so that the sheep and the horses and the cows have as much room to roam around as possible. What's the word before fence? Yeah, I know my writing is not the best. I'm sorry. Farmer has 120 feet of fence and wants to build a corral. To keep horses and cows separate, we also need a dividing fence. So it looks like this. So here's our corral, and there's a dividing fence in the middle. So they have equal space. So we want to make this thing. And typically when we're trying to optimize some sort of thing, we usually want to draw a picture. So here's that picture representing the corral with the dividing fence in the middle. So the first step is usually, maybe not always, but often to draw a picture. Draw a picture. And label it. So I want to label the sides of this fence because I don't actually know how long they are, right? I'm going to say, well, I'm going to call this side X, which means this side is also X. And I'm going to call this side Y, which means this side and this side are also Y. So for example, if I have 120 feet of fence, right, X could be 15 and Y could be, I'm not picking the answer. Let me make sure I'm not just picking the answer. Okay, I'm not. It'd be dumb if I just picked the answer like that. So X could be 15 and Y could be 30, right? And that would use up my 120 feet of fence. 15 feet here, 15 feet here, 30 here, here, and here. So it'd probably look more like this, really. Right? It would look kind of like that. Or this is 15, this is 15, this is 30. And the area of that corral would be 30 times 15, which is 450. But the problem is, how do I know if that's the maximum, right? Maybe there's a different configuration which gives us more area. And so what we need to do is we want to write an equation for the thing we're trying to optimize. So what are we trying to optimize here? We are trying to maximize the area enclosed. So the equation I'm going to write is area equal to base times height, or X times Y. So after you've drawn a picture and labeled it with variables, then we want an equation for the thing we're trying to maximize or minimize, optimize in general. Okay, now here's the thing. If you're trying to optimize something, it's usually going to be challenging to do so if it's a function of more than one variable. Here, the area is depending on both what the length of x and the length of y are. And that's going to make it really, really hard to deal with. So our job now is to find a constraint so that we can rewrite this equation in terms of just one variable. So typically, with optimization problems, there's some sort of constraining piece of information. It says we only have so much stuff. In this case, it's that we only have 120 feet of fence. So I need to write an equation that is kind of expressing that. So 120 feet of fence. So what that's going to mean for my corral is that this length plus this length plus this plus this plus this should add up to 120. I don't want to use less fence because I'm trying to get the most area possible. So I don't want to make it less than 120. I'm going to use all the fence. So I'm going to get 2x plus 3y is equal to 120. And I also want to solve for one of my variables. Actually, that's more part of step 4. So let me write those equations back. So we've got area is x times y, and 2x plus 3y. That is 120. Here's our picture. So now we want to solve our constraint for one variable, and we want to substitute into the other equation. Substitute in to the equation we're trying to optimize. So let me ask you guys, in this equation, should I solve for x or y? Or does it matter? Here it doesn't really matter, right? You could go either way. Sometimes there are going to be some equations where it's way easier to solve for one over the other. But in this case, it's pretty easy to solve for x or y. So I'm going to go ahead and solve for x. So solving for x, 2x plus 3y equals 120. Subtract 3y. And then divide everything by 2. So that x equals 120 divided by 2 is 60. And negative 3y divided by 2 is negative 3 halves y. And then we're going to plug that into this equation. So area equals x times y becomes area equal to x, which is this, times y. And then I'm going to multiply it out. So that area is equal to 60y minus 3 halves y squared. And here's the thing about the problems we are going to be seeing. When we talk about optimization, the only types of functions we really know how to optimize are parabolas, right? We know that this thing is a parabola, right? It's a quadratic equation, which means it has a vertex. And the vertex is either going to be the maximum or the minimum, depending on if it's opening upwards or downwards. In this case, since it's opening downwards, right, there's a negative coefficient on the square term. It's opening downwards, so we're going to have a maximum, which is what we expected to have, right? We're trying to maximize the area, so that makes some sense. So I kind of want to do two things here. I want to show you the fast way to solve it, but I also want to show you the meaning behind it. So let's talk about how to solve it first. So to solve it, we really just want to find the vertex. So I'm going to find the vertex in the usual easy way by finding the quote unquote x coordinate. Well, I should really say I'm trying to find the y coordinate of the vertex. And I feel like doing some graphing here actually would help a little bit. Of course, there's never enough room on this board, so I'm going to erase here. So I want to point out that the variables can be a little bit tricky sometimes. So if I look at the graph of this thing, y is actually my independent variable. It's going on my horizontal axis. And a for area is what's my dependent variable. It's going on my vertical axis. And if I was going to graph this, I mean, I know it's a parabola, I know it opens down. There's probably not more work I can do. But here's what it's going to look like. I know if I plug in 0 for y, I'm going to get 0 for a. Which makes sense, right? If y was 0, you would get 0 area. And then I also know that the biggest y can be is really 40. And the reason for that is if each of the y's was 40, that would be 120 feet of fence, and that would use up all the fence. 40 is my other horizontal axis intercept. Really, you could do some factoring and see that it's going to be 40. But if you plug in 40 here, you get 60 times 40 is 2,400 minus 3 halves times 1,600, which is also 2,400. So here's what it looks like. You know, it would continue on this way and this way. But the point is that this point here, where we have the y coordinate of the vertex, which is the x way. So the problem is the variables are confusing. I'm trying not to confuse you guys. So this is really a point y comma a, where the y is the usual x coordinate and the a is the usual y coordinate. And this value here, that's what we want. We want the quote unquote y coordinate of the vertex. So we're going to do the usual thing. We're going to find the x coordinate, which is negative b over 2a. And that's going to be, so if I look at this here, let me ask you guys a question. In this equation here, what's my b? Is it 60 or is it negative 3 halves? Yeah, it's definitely 60, even though it's written out of order. So my negative b over 2a is negative 60 over 2 times negative 3 halves, which is negative 60 over negative 3, which is positive 20. Which isn't surprising if we look at the thing I graphed over here, because the intercepts are 0 and 40. The vertex should occur exactly in the middle of that, which is at 20. And then we're going to find the a coordinate, the area, by plugging in 20 for y. So we're going to get 60 times 20 minus 3 halves times 20 squared, which is going to be 1,200 minus 3 halves times 400, which is going to be 1,200. 3 halves times 400, let's see, cancel a 2 there and a 2 there, is 3 times 200, which is 600. So we get 600. So here's what we are seeing. The vertex of this parabola, the input is the y value, which is just the length of this side, which is 20. And the output is the area, which is 600 square feet. Now here's the thing we have to pay attention to, which I would argue that I didn't in this problem. What did we ask for in the first place? If we go back, and I might not have written it super clearly. Now, I did not write it very clearly. I wrote, how should we construct so that we maximize area? The problem, if you read the problem that's in the notes, it actually asks what dimensions would maximize the area. So if we look at that version of the question, I haven't actually answered it yet, right? We found that y was 30. I think, no, we found that y was 20. Sorry, y was 20. Right, we definitely got that y was equal to 20. But we still have to find x. Fortunately, we have x written in terms of y right here. So we need to find x by plugging in y there. So we get 60 minus 3 halves times 20, which is 60 minus 3 halves times 20 is just 30, So we get x equal to 30. So the dimensions of this corral that maximize the area are this edge here having a length of 30 feet and this edge here having a length of 20 feet. That uses up all our fence, right? 30 plus 30 plus 20 plus 20 plus 20 is 120. And although it wasn't asked for, we also found that the maximum area was 600. The one thing I want to emphasize in this type of problem is that when you're finding the vertex of your parabola here, the quote unquote x coordinate is whatever variable is over here, right? So here the x coordinate was what y was equal to, and the y coordinate is whatever you're trying to maximize. In this case, it was the area. So typically, when we optimize things in this class, it's going to be some sort of work that's eventually going to lead to having an equation that's a quadratic, because quadratics are really the only kinds of things we are able to find the highest and lowest points of. Once we get to calculus, you will learn how to maximize and minimize other types of functions using more advanced techniques with derivatives. So this is definitely something you will do in your future as well, and there'll be a kind of an additional step to the process. So let's look at some more examples. So here we go. The company has determined that its total revenue in dollars for producing a product can be modeled by the following. So revenue in dollars can be modeled by R equal to negative x squared plus 450x plus 52,000. Please forgive me for not writing the entire question. It is definitely available on Canvas, and it definitely takes time to write it all out. So I think it's not too terrible just to write the pertinent information. Where x is the number of units produced and sold, yes. So the question is, how many units should we produce to yield the maximum revenue? So how many units will maximize revenue? And what is the maximum revenue? And I will point out, this problem is a little different than the previous problem in that a lot of it's already done for us, meaning we already have the thing we want to maximize. We don't really have a picture to draw here. There isn't like some shape we're trying to look at. So we know we are trying to maximize revenue, which is negative x squared plus 450x plus 52,000. And in this case, there isn't a constraint really, right? In the previous problem, we had some finite amount of material that was constraining our ability to build a larger and larger fence. Here we don't. Right? Here we just have that the revenue is equal to this function, and we can make as many x's as we want. But the problem is, eventually, if you make too many, you might have costs that we didn't really account for. So we want to maximize this function by finding the x value that's going to give us the most revenue. And hopefully, we can all see that this is a downward opening parabola, so that we're going to have a vertex that does have a maximum value. In fact, we'll probably graph in just a second here. So let's take a look. I want to find the vertex. The x coordinate is going to be negative b over 2a, which is negative 450 over 2 times negative 1. So 450 divided by 2 is 225. So what does that mean for us? It means that we should produce, so we want to produce X equal to 225 units. That is the number of units we need to produce that will maximize the revenue. What is that revenue? I don't know. We have to plug in X equal to 225 to figure it out. So if we plug it in, we're going to get that revenue is negative 225 squared plus 450 times 225 plus 52,000, which is kind of a big number, right? It's not the smallest number I've ever seen. I would probably use a calculator to do this. So getting out my calculator. So be careful here. When you do negative 225 squared, you're squaring first and then negative after. So it's 225 squared, and then the negative of that. So negative 50,625 plus 450 times 225, which is 50,625, and then plus another 52,000. So I'm getting 102,625. And that's how much, so that's my maximum revenue. If you want to show you the graph of this, just so you guys can kind of maybe believe me a little bit more. So let me show you real quick here. Yeah. Sorry, one sec, let me share my screen. Why don't we set the function equal to 0? So that's a good question. The reason we don't set equal to 0 is because that would tell us what the x-intercepts were. And it would also, we would be essentially setting the revenue equal to 0. And our job isn't to make $0. Our job is to make as many dollars in this capitalistic system that we're in, right? I mean, it's not the best example maybe, but the general idea is you're maximizing revenue. So we're trying to make this function have as large a y value as possible. And let me show you here. Let me plug this in. Get y equal to negative x squared. Sorry. So this is going to be kind of giant. So let me share it here with you guys. So hopefully you can see this here. Move this out of the way here. And you can't even see the function right now because we're in this kind of sense. So let's zoom way out. There it is. Wow, it's huge. It's a really, really narrow parabola, but we can zoom in a little bit and we can see the vertex of it right there. And look, there it is. The x value is 225 and the y value, or the revenue value, is exactly 102,625. So looking back, looking at a picture that you guys might be able to see a little bit better, if I draw it here, we've got something that looks like this, right? Where this point here has an x value of 225 and a y value of 102,625. So that's maximizing our revenue here. So I'm going to say this a lot, but when we're trying to maximize or minimize some function, if it's quadratic, you're really just looking for the vertex. And the important kind of distinction to make is which part of the vertex are you looking for? Are they asking you to find the x coordinate or the y coordinate or both? It kind of really depends on how the question's phrased. So let's look at some more examples. Let me find my examples. I lost them. I hid them from myself. I really hid them from myself. Come back. There we go. I got them. Okay. So let's look at the next one. All right. I'm going to try and be more clear about what I want. I will point out, Jonathan, to answer your question more fully, if we were tasked with graphing that parabola, we would totally find the x-intercepts by setting the whole thing equal to 0. But that wasn't really part of the question in that particular problem. So let's look at the next one. Oh, good. There's one. Let me know if you guys want me to join the group, but I will not join the group unless you specifically ask me to, and I will be fine with that. So only ask me to join if you want me to join. So here's the next problem. Find dimensions of the largest rectangle in the first quadrant that can be inscribed under the line y equals 18 minus 6x. So here's the line y equals 18 minus 6x. And here is a rectangle in the first quadrant that's inscribed under the line, meaning its corner just touches the line right there. And so I want to actually read the question. So find the dimensions. So find the dimensions of the rectangle that maximize the area. So I should probably label some things. I'm going to call that side x, that side y. And the area is given by x times y. And I really want to emphasize here that we're being asked to figure out what values for x and y are going to give us the most area. I also want to point out that here the labeling is kind of extra important that we do it the right way, because since we're working in the xy coordinate system, if we go over x and up y, this point here on the line is x comma y. And if the line is written this way, it is important that we don't interchange those in some strange way. So there's my equation, and I want to maximize this. I have a constraint. The constraint is that this rectangle is inscribed in this triangle, meaning that the bottom of the rectangle is on the x-axis, the left side of the rectangle is on the y-axis, and this corner here is within the triangle. And if you want to make the rectangle as big as possible, this corner should actually be somewhere on the hypotenuse of this triangle. So here's what our constraint really is. Our constraint is, in fact, that y is equal to 18 minus 6x. Right? If this corner of the rectangle is on this line, then you have to have the x and y satisfy the equation of the line. So great. We can throw that back into the equation for area. So we can say that area now is equal to x times 18 minus 6x, right? Where we're plugging in 18 minus 6x for y. And now we're going to multiply it out. So I get x times 18, 18x, x times negative 6x is negative 6x squared. And if it's important to you, you definitely can rewrite it so it's in the more usual order, where it's negative 6x squared plus 18x. All right. I want you guys to find the vertex. I'll give you a minute. think I made a mistake. I got negative 3/2. Oh yeah, I forgot a negative. It should be negative 18 over 2 times negative 6. And the way I knew I made a mistake was my answer didn't really make sense, right? For x to be negative would be kind of bizarre if I'm over here in this positive first quadrant here. So it's good to kind of think about if what you're getting corresponds to what you're drawing. So do I need to find the y coordinate of the vertex? This is a good question. And the answer here is actually no. So here's the thing, right? If I was going to graph this parabola, the x-axis would be x, but the y-axis would be the area. So it would look something like this, where this point here was the x-coordinate of 3/2, and the y-coordinate, or the area coordinate, of whatever the maximum area is. But the problem isn't asking us to find the maximum area. We certainly could. There's nothing wrong with that. But when I'm trying to do these homework problems, I'm usually trying to do not too much extra work that wasn't asked for. So if we look back at the question was, find the dimensions that maximize the area. So I know that x has to be 3/2. X being 3/2 will give us the most area. And then instead of figuring out what the area is, I'm just going to figure out what y is. So if x is equal to 3/2, y is going to equal 18 minus 6 times x, which is 18 minus 6 times 3/2. 6 times 3/2 is 9. That's going to be 18 minus 9, which is 9. So x is going to equal 3/2, and y is going to equal 9. Those are the values that will maximize the area. You can also use those then to find the area more easily, right? Instead of finding the vertex of the area equation by plugging in 3/2 for x here, which is a little bit of work, you can instead just multiply x times y and say the maximum area would be 3/2 times 9, which is 27/2. And that would be that coordinate of the vertex. So again, I just want to reiterate here, it is important to make sure we know that to be careful about what we're being asked to find, right? Here we were asked to find the dimensions, we only had to find x and y. We never actually had to find what the area value was. Although it's not wrong to find it, it's just not what we're being asked to find. Okay. Let's move on down to the next one. Well, that's a good problem. So we might actually have some time, because there's only one more problem. I guess I moved a little faster than I meant to. So if we have time at the end, I definitely can address questions you guys have, and I think we will have time because I only have one more problem to work on. So if you have a question after this next problem, you are welcome to ask it. So good question, Jonathan. So the answer is just 3/2 times 9. Well, not exactly. So the answer is, so the question was, find the dimensions to maximize the area. So the answer is really that the dimensions are x equals 3/2 and y equals 9. Or it might be slightly different if you label things differently, right? Maybe you decided to call this side L and this side W for length and width. And then you said this here was L comma W. And then your answer would have been L equal to 3/2 and Y equal to 9. So it does kind of depend on how you write your labeling in the first place. But I will say, the answer is not 27 halves. That is the maximum area, but that's not the question that we were being asked to answer. I feel like I had another good problem here. Okay. So let's look at the last one on the notes here. So the question here is, which point on the line y equals 3x plus 1 is closest to the point 2 comma 0? And you probably don't necessarily have to graph this one, but it's still nice to kind of graph it. So try and make a nice graph here. Here's the point 2 comma 0 and 3x plus 1. 3x plus 1 kind of looks like this. So I'm trying to find the point on this graph, which is closest to that point there. So it's probably around here-ish, but here's the idea. The way you find the point that's closest to another point is you try to minimize the distance between those 2 points. So I know this point here is 2 comma 0. I don't know what this point is here, right? This point could be any point on this line. It could be 0, 1. It could be -1, -2, right? There's lots of points it could be. Right, but what point is it actually? Well, we're going to set an equation to figure that out. So since I don't know what this point is, I'm going to give it a variable name. I would probably typically call it x comma y. But you can call it whatever you want. You call it AB, you can call it ZW, right? Any variables are fine. It's just X and Y are pretty typical. So we want to minimize the distance between the point XY and the point 2, 0. That's our job, to minimize the distance between those 2 points. Well, we talked about the distance equation. The distance is the square root of the difference in the x's squared, so x minus 2 squared, plus the difference in the y squared, which is y minus 0 squared. So a couple things here. Thing one, we have a function of 2 variables. So again, this is a situation where we need to eliminate either x or y. But again, we have a constraint. Our constraint is that the point xy is on this line. So if we know what x is, then we know that y is equal to 3 times x plus 1. So we can rewrite this as distance is equal to the square root of x minus 2 squared plus 3x plus 1 minus 0 squared. Oh, I don't need the minus 0, but okay. So I'm going to simplify this a little bit. So distance is equal to the square root of, so x minus 2 squared is x squared minus 4x plus 4. And 3x plus 1 minus 0, so 3x plus 1 squared is going to be 9x squared. I feel like that's right. 9x squared plus 6x plus 1. Right, all I'm doing is foiling it out using the pattern that a plus b squared is a squared plus 2ab plus b squared. I just shot water all over the floor. Great. Okay. So now look at this. I've got the distance is equal to the square root of x squared plus 9x squared is 10x squared. Negative 4x plus 6x is 2x. And 4 plus 1 is 5. I feel like this feels weird, but no, that's fine. Okay. So here's the thing. I want to figure out what makes this the smallest. But if you notice, the inside here is still a quadratic thing. So if I make the insides of this square root as small as possible, that'll make the square root as small as possible, right? It's because the square root is a function that gets bigger as the input is bigger and smaller as the input is smaller. So if I make just this part as small as possible, that will minimize the distance. So I'm out of room. I'm gonna go to the other side. I really miss having a lot more board to work with. Oh well, such is life. So this is something that's actually always true. Instead of minimizing or maximizing a square root of a thing, you can always minimize or maximize just the thing inside the square root. So instead of minimizing, I'm going to say minimize 10x squared plus 2x plus 5 instead of the square root of 10x squared plus 2x plus 5. And I should really say minimize the square of the distance. So we're trying to minimize this. We know how to minimize this, right? We can say it's a parabola. It's going to open upwards. It's going to look something like this. We're trying to find that point there, x comma d squared. Now really, if we look at the question again, before we get too deep into this, they're asking for just the point. So they're not actually asking us for what the minimum distance is. They're really just asking us for what's the x coordinate and the y coordinate. So I'm going to use this idea of finding the vertex of the parabola to find just the x coordinate. I'm not going to worry about the d squared coordinate, which is the y coordinate here. So the x coordinate is going to be negative b over 2a, which is negative 2 over 2 times 10, which is kind of funky. It's negative 1/10. And then we can find the y coordinate. Not by using this, but by going back to our picture here and say, okay, I'm looking for this point. X is negative 1/10. And we know that we're on this line, so y equals 3x plus 1. So x is negative 1/10. Y is going to be 3 times x plus 1. So that's going to be negative 3/10 plus 1, which is negative 3/10 plus 10/10, which is 7/10. So to answer the question that was asked, the point here that's closest is the point negative 1/10, comma 7/10. If we wanted to, we could also find the minimum distance by using the distance formula. It's not going to be nice, but we could do it. Or we could even, find the y coordinate of the vertex here and then take the square root of it. But again, that's not what we're being asked to do. So I will say for the last time today, it's really important that when you do these sorts of questions, you make sure you're answering the question that's being asked. And what I really want to make sure you guys, or state again, is that when you're thinking about the parabola here, right? Because all of these questions, eventually they're going to break down to having some sort of parabolic equation or some sort of quadratic equation where the x coordinate or whatever variable you're using that's acting like x in this equation right here, that's going to be one of the two things you're trying to find. And the y coordinate, or in this case, the d squared coordinate, that's going to be the thing that is being maximized or minimized. So if they're asking for the maximum or minimum value, you want to know what this is here. But if they're just asking for like the coordinates or the dimensions or the things that make it a maximum or a minimum, you're usually trying to find whatever the x coordinate of the vertex is. And then you're also going back to the thing you started with and looking at your constraint and plugging that x coordinate into that constraint to find the other coordinate or the other dimension. So, yeah. So I lied. I thought there would be time at the end. There's totally not time. I apologize. I got your hopes up, but I will now dash them. So we will talk more about optimization on Wednesday because it is an important topic. And I will probably reiterate a lot of the things I said today. This is definitely something you will do in calculus. Like there are definitely optimization problems you tackle in calculus. So this is a process you want to feel a little bit comfortable with moving forward. I will